This video will cover counting principles, which forms a small part of the maths syllabus. So obviously when we're looking at these notes, these first couple of diagrams, Venn diagrams, are just illustrating some conditional probability, which I talked about in my conditional probability video. Inclusive events, obviously when there's when there's an intersection between the circles, between the events. Mutually exclusive and exhaustive events, obviously no intersection, as well as no probability of something occurring outside of these two events given by I in this diagram. Just reiterating what exhaustive events are. Everything is either found in A or B, i.e. not A is equal to B. So this is clearly illustrated here. Not so if A is this circle, B is this circle, not A would be B. Then if you choose M objects to pair with N objects, then this can happen in M times by N ways, which is the fundamental counting principle. If you have 3 sock colors, 2 pant colors, and 3 shirt colors, how many combinations do you have? Therefore, you just multiply them all together and you'll come with 18 combinations. Then we look at arrangements without repeats. N objects are arranged without repeats. You use something called a factorial, which is basically this exclamation mark kind of thing. It can be found on your calculator so that you don't have to write out 6 times 5 times 4 and etc. So if we look at this example, take the word random. How many different ways can you arrange the letters without repetition? A crucial part of the entire conditional probability and counting principles section is to look for whether the question states without repetition or with repetition, because they are two very different things and require different working out. So looking at this question without repetition, all we're doing is we're saying how many letters do we have? How many letters do we have in this word? We have 6 letters. So in our first sort of letter space, we have 6 choices. Then in our second letter choice, we've used the one choice here, so we only have 5 choices. Then our third letter choice, we've used 2 of the choices out of the 6, so we only have 4, and that keeps going until you get 6 times 5 times 4 times 3 times 2 times 1, which is simply put as 6 factorial. Alright, then arrangements with repetition. This is a bit different in that it's not use factorials. If we look at the same example, random, the word random, how many different ways can you arrange the letters with repetition? All you're doing and saying is that you can have multiple repeats of the letters. So therefore, no matter where you put the letters, you always have 6 choices. So this will be 6 times 6 times 6 times 6 times 6 times 6, which is simply put is 6 to the power of 6. Then arrangements with choice, another fundamental section of this counting principles section. If we choose n objects from M without repetition, then m factorial over, then it's equal to m factorial over m minus n factorial. Note the brackets so that you do that sort of sum first before multiplying it factorially. So if we have 8 people running, how many ways can they be positioned in the top 3? So our first step is to look at this and say, okay, we have 8 people running, so in the beginning we have 8 people sort of qualifying for this position 1, and then because it's without repetition, we're sort of implying a factorial here. Then we go 7 and 6, which is just basically 8 factorial. However, 8 factorial would mean that it's 8 times 7 times 6 times 5 times 4. So we divide that by 8 minus 3 factorial. And this 3 factorial is because we're looking at 3 places of the possible 8 places. And we come to 8 factorial divided by 5 factorial. Then combinations with repeated choices. If we look at the word, so this is a question like this will always come up, guaranteed. If we look at the word dead, we can see that D is repeated twice. So how many ways can you arrange the letters to make a word? Interchanging the D's will give you a new word, but it's still the same word. So if you look at this, dead like that or dead like that, it's the same word, but the D's are swapped around. So all we have to do for this is similar to the last one. We take, how many letters are we working with? We're working with 4 letters, so it'll be 4 factorial, but then we need to look at our number of repeats. So how many times is D displayed? It's displayed 2 times, so we say 2 factorial. Then our final answer will simply be 4 factorial over 2 factorial, and that formula is given over here. Then if we look at a word like statistics, a little bit more complicated, how many words can be made from the letters in statistics? The first step, obviously, how many letters are we working with? We're working with 10 letters. Then we go and look for our repeats. So we say, okay, S is repeated 3 times, T is repeated 3 times, and I is also repeated 2 times. So then what we go and say is we say, okay, we're working with 10 letters, so we have 10 factorial, but we divide it by the repeats. So we divide it, we've got 3 S's, 3 T's, 2 I's, so 3 factorial, 3 factorial, 2 factorial, and these are multiplied together. And then we will get our answers. And then if we look at grouping, another section that can come up, so if we have 5 boys and 3 girls, and the partners must sit together, how many combinations can we make? So what I like to do is you draw it out to illustrate the combinations graphically, so that you're not just working with them in your head, because you will forget. So you can have a boy, girl, boy, girl, boy, girl, boy, boy, which will then in total is 8 people, because 5 boys, 3 girls. So here you have 5 combinations in essence, because the boy, girl, boy, girl, boy, girl are treated as one. So then you have 5 combinations, but the boy, girl can switch around to be girl, boy. So boy, girl can be girl, boy. So then what we have to do is say 5 factorial multiplied by 2 factorial. And the reason we have 3 sets of 2 factorials is because there's 3 sets of boy, girl. So all of them at one stage can change to girl, boy, if that makes sense. Then just a little aside, I haven't seen it, it's not very commonly tested, is the circle formation. So if they say something about people sitting in a circle, all you do is that you minus 1 from the factorial number. Counting principles and probability. So they can also link counting principles with probability. If we look at this example, the word history, what is the probability that the word will start with H and end with Y? So you've got to immediately be thinking to yourself, both the first position and the last position are locked, because there's only one possible choice for them. So just to help with some notation, the event that the word starts with H and ends in Y, I'm going to notate as E. And the sample space, so the total combinations, if there were no restrictions, I'll say as S. So I'll first jump to the sample space. So obviously, what you do here, because there's no repeats, it's simply the number of letters and then factorial, so 7 factorial, which gives you 5040. Then if we look at the event specifically with these restrictions of H in the beginning and Y at the end, we draw it. The best way is to just draw it out like this. So you say, okay, I've got that first letter has to automatically be an H, so there's only one choice, and the last letter has to be a Y, so there is only one choice. Then what we look at is we say, okay, we still have 1, 2, 3, 4, 5 letters in between out of the 7, that we can therefore go and use any other remaining 5 letters, so then that'll be a factorial. So this is like a hidden factorial inside these governed restrictions. And then what you do, remember that the question was asking for the probability, and what a lot of students do is they think, okay, cool, I've worked this whole thing out, but then they forget to go and work out the actual probability. So all you're doing is you taking your probability, your combinations that apply to your event where the restrictions are in place, divided by your combinations of your event when there are no restrictions. Simply put 120 over 5040, which you'll get at 0.023. Then just a number plate example. Number plate is formed with 3 letters of the alphabet and 3 numbers, excluding vowels. Calculate the probability of the following. So if we look at A, it starts with a B and ends with an S. So we've got to be looking at our whole entire sample space. So if we look at our letters section, so the 3 letters of the alphabet, we look at 20 letters because we're excluding vowels. Yeah, and then if we look at our next section here, we've got 10 possible single numbers, including 0 to 9. And we work at our sample space events being 800,000. Then we go and work out our combinations with the restriction in place, so starting with a B and ending with an S. So then again, your first letter and your last number will have to be a B. It's not an S, it's a 5 because it's a number. So your first letter will have to be a 5, will have to be a B, and your last number will have to be a 5. And then in between, you simply still have 20 options for your letters and 10 options for your numbers. And then what you do is you obviously just take your combinations with the restriction divided by your combinations with no restriction. Then if we look at B, probability of the number plate having exactly 1 B. So we say, okay, there's 3 possibilities here. They are illustrated here. Either the B can be first, the B can be second, or the B can be third. Your numbers stay the same, and the rest of your letters, you have 19 choices, because obviously you're using a B already and you can't repeat the B, so you take away 1 from the 20. And then you add these together and you get 1,083,000. Then what you do is you obviously use your sample space, and very often these questions are linked to each other. So take note that if you've already worked out your sample combinations, just carry them through to here, divide the one by the other, and you get your probability. Then if we look at C, number plate at least 1S. So at least 1S, there's a clever way to doing this, because the long way is you either say, okay, 1S, 2S, 2 S's or 3 S's, or what you can do is you can apply this formula, which you can say the probability of at least 1S is equal to 1, because the total probabilities always add up to 1, minus the probability of no S's. So then, sorry, just going back to that, it's not an S, it's a 5, sorry. So then what you would do is you'd say 1 minus the probability of no 5s being included, and that will be demonstrated over here. All your letters are included, but then you only have 9 choices for your numbers. And then your sample space you're using from here, you've already worked it out. Divide the one by the other, you'll get 0.729. But remember, this is the probability of there being no S. So then the probability of at least 1 S is 1 minus that answer, and then you will get 0.271. That concludes the video for counting principles.